Hello! Let's do some calculus. We are on daily lessons 189 and 190. Let's do this thing. So this is, well, it says ant differentiation. That's not right. Anti-differentiation. There we go. By U substitution. So in the examples that we had above, and so it says above, but really on the previous pages, we could find g prime of x, whatever the inside function was of a composite function. So if I had something that looked like this, g prime of x, and then I had over here at f prime of g of x, something like that, I could recognize this function, like the derivative was here of whatever this function was on the inside, and recognize that this would just be f of x plus c. And we might have to manipulate a coefficient of some sort, but it was okay. Overall, we knew what to do. So this was on the previous pages. We could do this by pattern recognition, that we just were like, okay, we took a guess and then we checked to see what the antiderivative was. There's going to be some problems like this. If I tried to find the antiderivative, right now, the stuff on the inside, the derivative of 2x minus 1 is 2. But I have this extra x out here. So in these cases, we can't use pattern recognition because typical chain rule has not been applied. Something weird is going on here. So the only thing that we can do is use what we call U substitution. So we're changing the variables around. So these blocks are going to help us just really think about how to do that and organize our thoughts, and then eventually we'll take those, just that scaffolding away where you'll be doing this without those blocks. Okay, so identify the inner function g of x. So right now, when we were talking about the inner function g of x, it was like what was on the inside of some composite function. So if it was like f of g of x that we're starting with, or, sorry, I really should have said f of g of x over here, plus c, whatever we were starting with, the stuff on the inside. This, we're going to recognize the stuff on the inside of the function. So this, I'm going to say that's 2x minus 1. If I took the derivative of that, I would just get 2. Is g prime of x part of the integral? The integral is the stuff between this integral symbol and the dx. Is it part of this? We would say no. Is g prime of x attainable by multiplying by the integrand, or I'm sorry, is g prime of x attainable by multiplying the integrand by a constant? Well, we could multiply by 1/2, but we somehow get this weird x, so we would say no. I can't multiply 2 by something to get x. So this isn't okay. So here we're going to find the antiderivative by a method used as known as U substitution. So we're going to use this function up here. U is the inner function, so the stuff inside the inside. So I can see I have a function and it's cubed. The stuff on the inside, I'm just going to say is U is equal to 2x minus 1. And then it says find du and solve the equation for dx. What's going to happen is that all the x's are up here are going to become u's, but if I just changed it to a different variable, it wouldn't help me. I need to actually change the function itself in the way that it looks so I can find the antiderivative. So bear with me on this one so you can see what's happening. It says find du. So the derivative of u is 1 du dx. Because I'm going to do this in terms of x, so I can say the derivative of u with respect to x, du dx. This is the same thing if we were taking the derivative of y, we would get dy dx. Same idea here. Really important you write it this way and not as u prime, and you'll see why in a second. On the right, the derivative of 2x minus 1 would be 2. And then you can write dx dx, but that's really not important. So the reason why this is so important is because I actually want to replace this integral. So I want to change how it's written. So right now I can see I've got an x, 2x minus 1 to the third. Well, I know 2x minus 1 is u. It's still to the third. And notice I'm not doing anything right here. I'm not just writing down x again. We'll see what that is in a second. But you see how out here I have this dx? I want to replace this in some way. And so what I'm going to do is I'm going to solve for dx over here. So normally we think of this as du dx and they are together. I can actually separate these by multiplying both sides by dx. I get du is equal to 2dx. I want to solve for dx, get it by itself. So I'm going to divide both sides. Or I could say multiply by 1/2. So I can say dx is equal to 1/2 du. So over here, when I have this dx, instead of writing a dx, I'm going to write 1/2 du. So I'm changing things out within the function. So I'm saying u to the third, since u was 2x minus 1. The dx, when I solve for this, when I actually take the derivative of this function up here, so I've got u, and I take the derivative of that, I get du dx is equal to 2. Multiply both sides by dx, solve for dx, I'm substituting. The last thing I'm left with is replacing this x. And I know right now that u is equal to 2x minus 1. So if u is equal to 2x minus 1, I would add 1 on both sides. Divide by 2. And I'm just going to rewrite this as x would equal 1/2 u plus 1/2. That means over here, instead of an x, I'm going to write 1/2 u plus 1/2. And remember, x was multiplied by this entire thing, so I need to remember parentheses. And you might be saying at this point, why do I care? What am I doing with this? So if that's you, it's okay. Thank you for not messaging me in those comments or anything right now. But what's happening now is I can simplify this into something that I can take the derivative of. So what I'm going to do is I'm going to take this 1/2 u to the third power and distribute that. So I'm going to have 1/4 u, because 1/2 times 1/2 is 1/4. U times u to the third is u to the fourth. Plus 1/2 times 1/2 would be 1/4. And then there's just a u to the third left over. So do you see how now I have this really nice integral? I've got the integral of 1/4 u to the u to the fourth plus 1/4 u to the third. If you were like, I want to just get rid of these 1/4s because I can see both of them have a 1/4 and write that in front of the integral, that's totally fine to do. If you're like, let's just keep going with what I have, you can do that also. You need to know that both are possible. So it is okay if you were to rewrite it like this. So that would be acceptable. This means the same thing as that. You can always pull a constant out in front. But if I just stick with this, like, okay, how do I integrate this? I add 1 to my exponent. This would be u to the fifth. I divide by my new exponent. So 1/4 divided by 5 is the same as 1/4 times 1/5, 1/20th. U started as u to the third. I'm going to add 1 to the exponent. Divide by my new exponent. So 1/4 divided by 4 be 1/16. And then this is it. This is all I have right now, plus c. And you might be thinking, weren't we integrating this mess? This doesn't look anything like this. We can do one more step. We can say 1/20th. You know how I said u before was 2x minus 1? Ta-da! And really, if you wanted to see how was that possible, you could have taken 2x minus 1 times 2x minus 1 times 2x minus 1, multiplied that all by x, and then done the antiderivative this way. And you would get the same thing as we got right here, except you would get some really gross answers that would need a whole lot of simplifying. So this is where we're at. Okay. At this point, I know it's a lot, so just bear with me. If you can't see whatever the derivative is of this on the inside, if you see there's another variable out here, like, or it's the wrong power for some reason, like if, let's say I had x to the third in here, but there wasn't an x squared on the outside anywhere, this is what we have to do. We have to use substitution. Let's try 2 more together. The really tricky part of this is trying to figure out what is the thing that's causing the problem. So if I were to rewrite this and just try to do this by hand first, I would say 2x plus 1, x plus 4 to the 1/2 power, negative 1/2, excuse me, because the square root is in the denominator. And I would think, okay, this is the thing that's like stuck inside of another function. I've got something raised to the negative 1/2 power. If I were to raise this to the 1/2 power, divide by my new exponent, like go through all the antiderivative rules. The problem is the derivative of the inside is just 1. Over here, we've got a 2x plus 1. So that's an issue. This isn't a standard chain rule problem. So we take the thing inside of, in this case, the square root, and or I can say inside the negative 1/2. This would be like, if I have a function within a function, this is the stuff on the inside. So that's what I'm going to set u equal to x plus 4. If you want to start this right away and you want to say, you know what, I want to integrate, and over here, square root of u, and write that right away, do that. That's totally okay. Now it says find du and solve the equation for dx. So I'm trying to get rid of this part of my integral, or at least exchange it out to be something nicer. The derivative of u is du dx. The derivative of x plus 4 would be 1. That's nice. If I multiply both sides by dx here, I've got du is equal to dx. So just over here, instead of dx, I can write in du. One more problem. I've got 2x plus 1, and I want this in terms of u instead. Well, I know u is equal to x plus 4. That means x would be u minus 4. So if I'm going up here, I've got 2 times the quantity u minus 4 plus 1. And you might be thinking, I still can't take the derivative of that. But there's a little bit more we can do with this. We could rewrite this, and we could say, I'm going to say u to the 1/2 in the denominator instead. And I'm going to be able to divide every term in the numerator by u to the 1/2 to simplify. Up here, this would be the same thing as 2u, and then I would have minus 8 plus 1. If I say, what does that equal now? 2u divided by u to the 1/2. And I'll even do one more step so you can see where this is coming from. I'm taking each part and dividing this by u to the 1/2. This would become, this is u to the first, subtract the exponents because I have like bases. This would be 2u to the 1/2 power. This is going to be plus 7u to the negative 1/2. In parentheses, because this is all my function, times du. Now find the antiderivative, because now I've got this in something that kind of looks like a polynomial. There's weird exponents, but kind of. Add 1 to my new exponent, so I've got 1/2. My new exponent would be 1/2 plus 2 over 2, which would be 3 over 2. If I take 2 divided by 3 over 2, that's the same as 2 times 2/3. I should get 4/3. And then if I do another one, what's this one? Plus u. My new exponent, u to the negative 1/2, add 1 to that, you get positive 1/2. 7 divided by 1/2 is the same as 7 times 2 over 1. And then don't forget plus c. If you keep it up here and you say u is equal to x plus 4, this is your answer. Or if you want to go one more and you could say, well, 4/3, I know u was actually x plus 4. We have the antiderivative. So So the antiderivative of this is that whole mess. And you could actually, if you're like, I don't believe you, take the derivative, simplify. It'll come down to this. In the next step, this one says, find the value from 1 to 5 of this integral. And you're like, I don't know how to do that. This one was plus c. This is called an indefinite integral. This wasn't from one place to another. But remember what this definite integral means. It'd be the area under the curve from 1 to 5 of this function. And so there is a way to do this in your calculator. We'll do this in a second when we check our results using the graphing calculator. But this one, the way that we find the antiderivative and then do f of b minus f of a, fundamental theorem of calculus, we can't do it the way it's written right now. Because the stuff on the inside, if I took 2x minus 1, took the derivative, it doesn't give me a derivative of x. So I have to use u substitution. So I'm going to go through that same process. I don't have the blocks, but I'm going to do the same thing. I'm going to say, well, what could u possibly be? The stuff that complicates the function, that I can't simplify in some way. It's the stuff within the inside here of whatever was raised to the 1/2 power. So I've got 2x minus 1. And if I integrate this over here, I'm going to ignore these numbers for a second and you'll see why. But this would be the square root of u. The next thing I want to do is find, instead of dx, take the derivative. The derivative of 2x minus 1 would be 2. If I solve this for dx, we get du is equal to 2 dx. I can divide. So dx is actually equal to 1/2 du. Over here, instead of dx, I'm going to put in 1/2 du. If you want to automatically take this 1/2 out into the front, you can, because it's going to be multiplied by everything here. Remember, I still have this x. If u is equal to 2x minus 1, that means u plus 1 is equal to 2x. And I'm going to write this just because I know I'm going to need to multiply in a second as 1/2 u plus 1/2. I did not give myself a lot of room. And I still have to work with this. This is where you've got an option. You know at the end how we multiplied, or we took this back into like what x was going to be, or in terms of x and instead of terms of u? If you don't want to do that last step in definite integrals, what you can do is, right now this is from x equals 1 to x equals 5. If we want to make it easier and not have to do that last step on my antiderivative, I can change this right now to be this u. So right now it says an x. But if I want it as a u instead, if 1 is equal to x, 2 times 1 is 2, minus 1 is 1. Right now I've got, I kind of wrote over this, but 5 is equal to x. 2 times 5 is 10, minus 1 is 9. Now everything's in terms of u, so when I do the antiderivative and then I say f of b minus f of a, I don't even have to change it back to x's because I already changed these limits of integration. Okay, I'm going to rewrite this as 1/2 u to the 1/2, or plus 1/2. But I'm going to change this to u to the 1/2. Because now I can see if I distribute this, I would get 1/4 u. Remember, when you're multiplying with like bases, you add the exponents. So 1 plus 1/2 would be 3/2. 1/2 times 1/2 is 1/4. U to the, this would just be 1/2 because it was just a 1/2 times that whole thing. If you want to bring 1/4 out in front, you could right now. If you're like, I just want to keep going with this, what you're going to do is you're taking the antiderivative so that you can do the fundamental theorem of calculus. So add 1 to the exponent. This would be 5/2. Gross, but okay. 1/4 divided by 5/2 is the same thing as 1/4 times 4/5. So I have 1/5 plus my new exponent, 1/2 plus 1 whole would be 3/2. 1/4 divided by 3/2 is the same thing as 1/4 times 2/3. This would be 1/6. I'm just checking with the old me, making sure I got the same thing. Hey, I did. And then instead of a plus c here, because this is a definite integral, it started at one place and ended in another, we're going to evaluate this from 1 to 9. F of b minus f of a. Think about this. So I'm going to say, just so you can get into this, there's nothing labeled as f, so I'm just doing this to help me. The function value at 9 minus the function value at 1. And here I should have definitely saved myself some room because this is not going to look all that nice. F of 9, I'll put right down here. Oh, I definitely should have saved some room. So what I'm doing is the function value at 9. And you would end up doing, hold on, I have 1/5 here. Why did I do that? One-fifth divided by 5/2 is times 2/5. Silly me, so this should have been 1/10. There we go. So I'm going to say 1/10. Should use a different color. There we go. This is where I'm actually substituting in. So 1/10. 9 to the 5/2 power plus 1/6, 9 to the 3/2 power, minus, and now I'm going to substitute in 1. 1/10, 1 to the 5/2 power, which is just going to be 1, plus 1/6, 1 to the 3/2 power, which is going to be 1. This is gross, but one more thing I want to show you before I give you what this answer actually is. If you take 9 to the 5/2 power, the square root of 9, because this is 5/2, think about 9 to the 1/2 power would be the square root of 9, which is 3. This is the same idea, but then it would be 3. So 9, the square root of 9 is 3 to the 5th power is 243 over 10. This is disgusting. 9 to the 3/2 power, you would take the square root of 9, which is 3 cubed, 27. 27 over 6. Ew, who's your teacher that assigned this? This would be 1/10 plus 1/6. And actually, I can see something going on here. Do you see how this is 243 over 10 and then minus 1/10? You could put these together first. This would be 242 over 10. I'm going to go over here because I'm running out of room. 242 over 10. And then this would be plus 28 over 6. Do I even want to do this? Oh, sorry. 242 over 10. Oh, 27 minus 1 is 26 over 6. Gross. And I think I did this in my calculator before. After all that work to do it in the calculator, but you get this. So it's a ton of work, and usually if you have to do this by hand, the numbers are nicer. But just to show you that yes, we are doing this correctly, and this is what it is say it is. So I get an answer of 28.533. You're like, why did we do this if I could have used my calculator all the time? Because you're learning the process for other types of problems. But if I go into math, and then I'm going to go down to where it says the f integral function integrate, that's 9, and I'm going to do the original function from 1 to 5, and I have x square root of 2x minus 1. Don't forget the dx at the end. Hey, we got the same thing. That's exciting. Okay. I know this is a lot. Use substitution, whether we're in the classroom or on here, is really difficult. It's just going through this step by step. Some people are actually going to really like this because it has a set order and it's predictable and it works every time. Whereas pattern recognition, it's sometimes easier, but it can change and you have to be really careful with the coefficients and what to do. And there's kind of like it's more of a guess and check. This one's a sure thing. So hopefully you like this a little bit better. Thanks for learning. I appreciate it. Have a great day. Bye.